Okay, well, let's go ahead and get started with lecture Tuesday, April 14th. This is Geo 420 Hydrogeology. Okay, so first day back from the exam. I haven't graded any exams yet, so I have no idea how they went, but everybody turned something in. I'd say the delivery of online exams is harder than I thought. But seemed like everybody turned something in, and we'll see how they turn out. I hope to have them graded by Thursday. We'll hand them back out. I wanted to cover some other course business while we're at it here. So the first thing I wanted to do was to talk about the final project. And I've posted, so there's a couple things I've done here. I've changed our final project. To one I think will be a little easier to get done remotely. And then and I've posted that onto Moodle, but I wanted to just go over it here with you guys right now. So I'm going to share my screen here and we can have a look at the final project. Okay, so why is this down here? Are you guys seeing my screen? Yeah?
Yeah, I can see.
I don't know why my Zoom bar is like in the middle. I don't know if it's showing up for you guys, but hang on one sec. I'm gonna stop this for a second. Share it again. All right. There we go. Okay. So the bottom line is the final project is a paper. What I want you to do is basically, well, my learning objectives here are for you guys to read some hydrogeologic reports and synthesize that data. So use what you've learned to understand first what the report is saying, and then synthesize that data to be able to develop a conceptual model of a groundwater system. And so what this really is a desktop hydrogeologic investigation. And this is, step one of any hydrogeology project is to go out and find out what other folks have done in the area and start to develop your own conceptual model of the hydrogeology of the system. So what I want you guys to do is write a report on the hydrogeology of the city or the county where you grew up. All right. These reports we'll talk about the format more, but bottom line is no longer than 10 pages. All right. I don't want you guys to write to a length, but I'm going to cap it. I'm not going to read more than 10 pages. Your final objective here is to develop a conceptual model, and we're going to talk a lot about what that means. But a conceptual model is essentially, you could simplify it to thinking about like a cartoon drawing of the groundwater system that contains all the ingredients for the boundary value problem. So where are my boundaries? What kind of boundary conditions do I have? What is the layerings or the stratigraphy? Where are the aquifers? And what are the parameters of those aquifers? So hydraulic conductivity, storativity, porosity, parameters that we need to know for all the aquifers. So from here on out, a lot of the class is about characterization. So how do we go in and characterize these groundwater systems and describe them and investigate them? So what you're going to be doing is taking a lot of what we're using over the next few weeks and putting it, sort of stitching it all together to make your own conceptual model. All right, so the default is the place where you grew up. I have a caveat here. So if you're a graduate student, there's a few of you in class. I actually think that many of you, it would be very helpful for your research to do this for your research area. All right, so this would be creating and looking and developing your hydrogeologic conceptual model for your research area, rather than where you grew up. Now, if you're not a graduate student and you still have a research area and you'd rather do it for that research area, I don't necessarily care. Okay. So you don't have to do it where you grew up. I just kind of think it's interesting. But you know, if you have a research area, do it where it's most useful for you. Okay, paper format is roughly follows a USGS water resources investigation. So hopefully you'll read some of these. If you're talking about a groundwater system in Ireland, you're not going to have a USGS water resource investigation. But if you follow this, we'll talk about the sections you need. You just follow these sections, then you'll be fine. Okay, so when we write a scientific report, we cite references, and you gotta choose a citation style. We're going to use the citation style of the American Geophysical Union, which is really common throughout the geosciences. And I've given you a link. You can just see what they look like. It's basically our author year. All right, so it's the last name of the author and the year it was published. And there's a whole guide to how you do that. All right, so the sections that you'll need to come up with. So the first is geologic setting. So we need to know, I don't need necessarily a geologic history from the beginning of the Earth to present time. But you do need to give us enough geologic history so that we understand the formations, how old they are, what sort of environments they were deposited in, and the general history, so we understand the stratigraphy and the sequence. So geologic setting, enough so that we understand this next section, and that is the hydrostratigraphy or the hydrogeology. So this is essentially, what are the major formations in the area, the major aquifers, and confining units? So at the end of sort of this section, we should know what is the geologic structure of the area look like, and what are the major aquifers and confining units. Then we go in and we talk about the principal aquifers that are used, right? So now we're going to focus in. We've sort of set the stage, and we're going to focus in on the principal aquifers. So what kind are they? Are they unconfined? Are they confined? What kind of the characteristics? And by characteristics, I want you to look for things like hydraulic conductivity, thickness, porosity, storage values. And so the basic quality and size of these aquifers are what you're going to do here. You're going to characterize the principal aquifers that are utilized in the area. And then finally, you're going to do a water resources section. And so for these principal aquifers, you're going to look for, you're going to try and create basic water budgets. So what are the sources and the volume of recharge and discharge to the aquifers? What are the quantities of groundwater usage in the area? So how much is used for irrigation, municipal or household use, and industrial use? And then finally, a statement about what's the changes in storage. So are we drawing this aquifer down? Is it staying steady? Could be that the head and the water levels are increasing. So I want some investigation into what's happening for the changes in storage. All right. I will post some examples of previous papers on the Moodle site as well. This project description is on the Moodle site. Oh, a note about sources. All right, so the sources of information that you can use to develop your conceptual model are those that we would typically use if we were writing a professional report. So those can be peer-reviewed journal articles, professional reports, so national or state geologic survey or water resource reports, and then consulting reports. So there may be consultants who have done work in the area. Okay, so if you're working in the US, I've given you a really good starting place, and that's the National Groundwater Atlas. That's published by the USGS, and they have essentially for each region, they break down the basic hydrogeology, all right, of that area. Now, this won't be the only source you can use. It's a place to get started. There will be often citations within the atlas that will lead you to be able to just follow those citations to get other sources of information, but it's a good starting place. I don't know whether there's a similar product for Ireland or not. So I'm not sure, but I would guess there's something like that. They know somebody's got some broad overview, of the hydrogeology of Ireland. I mean, it's like smaller than Montana, so surely somebody's done it.
Yeah, we have the Geological Survey of Ireland has groundwater management and bodies for all the counties and towns.
Okay, cool.
So we have it all there anyway, I think. Well, some of it. I haven't looked too much into it, but we have some.
Yeah, well, you'll find out what you actually have. Okay, so that's the final project in a nutshell. We will be, I will make it do let's see, finals week is the 4th. So right now, tentatively, I have it due at the starting of finals, so May 4th. Okay, so questions on the final project?
Yeah, I was going to ask, can we use our own data?
You can
If we
use
some-
well, yes. If you're doing research in the area, you can use your own data.
Cool.
Yep. Now, if that data came from another source, you need to cite that source.
Right. Okay.
Okay. So that's the term paper in a nutshell. Okay, so the second business item is the final homework assignment, homework 4. I've pretty much got it put together. So I will post that after class. All right, so homework 4 will be available to get started on after class. Okay, so final project, homework assignment. I think that's most of the business I wanted to cover. In which case, we'll get started on thinking about our next topic, which is going to be groundwater stream water interactions. Okay, so I first want to just discuss the types of groundwater stream water interactions we can have and just some basic vocabulary. So I'm going to draw a few cross sections of streams. So here's our land surface, stream channel, land surface. And here's the stream. Okay, so the first type of stream we'll discuss is one where the water table slopes upward away from the stream. All right, and so groundwater flows from high potential to low potential. So it flows from the adjacent area and into the stream. All right, so this stream is gaining stream gains groundwater. So we call this kind of reach a gaining a gaining stream. All right, so water table is higher away from stream. All right, so this is type 1 gaining stream. All right, so let's consider another situation where now we have our cross section. Now this time, the water table slopes down away from our stream. All right, and again, water flows from high potential to low potential. So now water is flowing from the stream out into our groundwater system. All right, so water table is lower. Away from the stream. And this, so this stream loses to groundwater. So we call this a losing stream. And by the way, this goes for a lake as well. So I'll put a lake here, any surface water body. All right, so these are our sort of two end members. We can either gain from groundwater or we can lose to the groundwater. So we either have a gaining surface water body or a losing surface water body. But we can get some variations on this. So if I now consider another cross section. Uh-oh, I've clicked the crazy button. I can have my water table beneath the level of my stream. All right, so my stream is losing, but I have an unsaturated zone between the stream and the water table. All right, so this we'll call 2A. we're losing, so it's a losing reach, but it's not connected. The water table is not connected. So we would call this one losing not loosing.
Does that happen a lot with irrigation ditches?
Yeah, it can happen with irrigation ditches. Where it happens a lot in Montana is where streams come out of the mountain block and into a big alluvial valley. So, for example, where Lolo Creek comes out of the Lolo Canyon and into the Bitterroot Valley, or any of those Bitterroot streams come out of the Bitterroot mountain block and out into the Bitterroot Valley, they're often losing disconnected. So here they lose very rapidly generally to the water table.
Sir, wouldn't, because you said that it's a Valdose portion, would the water table also give off some water? So it would be kind of like in both directions?
You mean, would the water table give water back up to the stream?
Yes.
No. Nope. In this, because the reason why is if I put a piezometer in the stream, the water level is going to rise to the water level of the stream. If I put a piezometer in the water table, the water levels, or in the groundwater system, the water table is going to rise to the level of the water table. So the potential is downward only. You will only move fluid from the stream to the groundwater table.
Okay, so the capillary action, the capillary action is only in one direction then?
The capillary, there may be a capillary fringe here, but it won't draw water into the stream.
Okay.
Okay, so we can have losing connected. So this one is losing connected, and this is losing disconnected. All right. So one of the challenges here is if I come out here and I drill a well, all right, what I do is I measure the water level and it's here. And I say, well, that seems to be lower than my stream, all right? But I could either be in a losing connected or a losing disconnected stream. I really have no idea. So it's quite hard to tell the difference. Okay, so losing and losing disconnected. There's another type that we generally consider, and that is a situation where the water table is higher on one side of the stream and lower on the other. So we've got a situation where the stream may gain groundwater from one side and lose to the other. And so the groundwater, we can think of this as groundwater essentially flowing through our stream or lake, all right? So groundwater flows through, so we call this a flow through. All right, and here the water table's higher on one side. And lower on the other. All right, so these are, I'm going to call them three major types, gaining, losing, and flow through. Now I want to investigate these types a little more. And in particular, I want to look at what they look like in plan view. So we're going to start off here with a gaining reach. All right, and now I'm looking down in map view. And I've got a stream running through here, and let's say that the stream is going this way down the screen. All right, and I want to look at the shape of the water table around the stream using potentiometric contours or head contours. All right, so each of these red lines is a head contour. All right, now if my stream is gaining, then water's going to flow, groundwater's going to flow into my stream. My stream looks like a valley in the potentiometric surface. That directs water flow in. So let's look at, so let's say, let me label some of these. Let's say, I don't know, this one's 10, this one's 9, 8, 7, 6. Whatever unit you want it to be in. We'll put it in meters. So these are values of the groundwater head, contours of the groundwater head. So now let's draw a few flow lines. right? They have to intersect our head contours at perpendicular angles, right? So they would follow these contours into my stream, and I would have a gaining reach. All right, so this is this V pattern here. This pattern here is the classic gaining reach pattern. All right, so this is map view of a gaining reach. Now let's go down and consider a losing reach. All right, and again, I'm going to draw a map view plane. Stream moving down through our reach. And here's our head contours. Now it's going to be the opposite here, where my stream is going to look like a ridge. Oh wait, what have I done? Yeah, this is okay.
You mean a valley, sir?
No, this is now going to be a ridge. Okay, so now let's follow some flow paths. All right. They would tend to bring water away from the river. So we would have flow paths that originate at the river and move out. All right, so this is the losing reach pattern. Where our stream is a ridge in the potentiometric surface, and it is driving water away from the stream, all right, and out into the alluvial plain. All right, and then finally, let's do a flow through reach. So I'll draw again a map view plane. Stream moving through it. And now if I do some flow paths here, they would come in on one side and they would leave on the other. Come in and leave. So one of the key things so when we have a gaining or a losing, we have some sense of symmetry. So it's almost like the stream's a mirror here, and you could reflect these contours on either side, but we don't have that symmetry on on a flow through reach. So there's no symmetry. And the water's just moving through the reach. Okay, so these are the basic patterns when we look at elevation and contours in head around a stream. These are the basic patterns that we're looking for to determine whether they're gaining or losing, right? And it's really important to be able to draw these flow nets, all right, so that we can understand which way the water's moving, all right? So when you see a contour map, we follow our rules of flow nets, all right, that we flow from high potential to low. And again, these would be 10, 9, 8, 7, 6, all right? And we intersect, our flow paths intersect our head contours at roughly right angles, all right? So what's the value of the head in the stream right here? Or the elevation of the water level in the stream right here?
Would it be 9?
Yeah, it's 9. All right, so one thing that's important to remember is where this contour crosses the stream, that's the elevation of the water level in the stream at that point. Okay, so let's think about what we know about streams. Does this elevation in this stream stay constant? Like if I
No.
come here and is the water level in the stream going to be 9 meters all the time?
No.
No. It's stream levels vary all the time. So for those of you who are in Missoula right now, the Clark Fork is turning brown, water levels are rising, all right? So one thing that's important to remember with these interactions is that they change dynamically with time. All right, so we can think about what's happening in our streams right now in Montana. All right, so I went out and ran some errands on Sunday, and I noticed it was the first day the Clark Fork has turned brown of the spring. So for a long time, for all winter, our water level was low. Our groundwater has been feeding our streams. All right. So we were all winter, the majority of these streams were gaining. Okay. Now we're melting snow up high. All right. And we're flowing water down into the Missoula Valley or down into these adjacent valleys. And we're increasing the water level in our stream. What that does is move groundwater out into the banks. And we are creating right now a temporarily losing stream. So right now we've reversed the flow and we are moving water out of the stream and into the groundwater system. This zone right here where we move the ground or the stream water out into the banks, all right, during these increases in stream flow, this is called bank storage. All right, we're temporarily flooding this water out into the stream. We're creating a temporary losing reach, all right? And we'll do that for most of the freshet. We'll move water out into the adjacent alluvial aquifers during the freshet. We'll fill them. And then when we come back sometime later, say in July, as the water level starts to recede. So this here is, we'll call this May. All right. As the water level starts to recede, in July, the water level comes back down, and our new bank storage water will come back into the stream. So we dynamically store water in the banks and then release it . So say this is July. All right, so now we're releasing that water that we stored in the banks, and the stream levels dropped again, and we're now a losing reach again. So we change from gaining, sorry. we change in May right now, we're losing and storing water to gaining reaches later in the summer.
So, sir,
Yep.
the snow melt, most of it goes into the Clark Fork instead of into the aquifer itself.
Well, it depends on where you're at. So is there any snow left in the Missoula Valley right now or any of these valleys?
Not really.
No,
I mean,
that's
we
all
still
gone.
have a lot up. We have a lot up in like Lolo and the surrounding area. but-
Right. All the snow is left is up high. So we're melting high elevation snow. It's flowing down these stream networks. All right. And as it does that, it raises the water table or the water level, sorry, in the stream. So in these lowlands, the stream level is above the groundwater level because the snow's all gone and we're losing. Now,
So
the
that's why the
story is
Clark-
different up high where the snow melt is occurring.
Okay, so that's why the Clark Fork turns brown, because we have a lot of interflow that's carrying a lot of sediment. With it?
The Clark Fork's turning brown because as the water level rises, it's picking up all the sediment from the banks that has
Okay.
been sort of deposited over the year.
Okay,
But so one thing that, okay, so first of all, we expect these changes to, or these, whether the thing's gaining or losing is very dynamic, all right? So for sure, we see this big seasonal change here in Montana, but in other places where you don't get snow melt, you still get storm-driven changes in gaining or losing, all right? So they change dynamically. We can change on a daily basis whether we're gaining or losing. Okay, so these interactions can change rapidly and are very dependent upon the water level in the stream, and that's a function of how much precipitation, evapotranspiration, and other processes are occurring. The other thing that's important to think about is that they change, especially with streams, interaction type changes in space. So I'm gonna draw in map view now a stream. And make my swiggle smaller to make it seem like this is at bigger scale. All right. And we could easily have portions of the stream that are gaining. Losing. Flow through. Back to gaining. Do another losing section here. Do a flow through. So let's let's do some flow paths here. Well, these ones would be coming in to my stream. These ones would be losing, gaining, losing, gaining, losing, flow through, losing, gone. Maybe this one just comes in, intersects the river, and leaves again. All right, so this is a really typical thing when you actually look at a potentiometric surface of a river. You're not going to have, the whole river is not gaining or losing. You have reaches. So this would be a gaining reach. This would be a losing reach. This now here is another gaining reach. Down here, we got a flow through reach. All right, so these interactions types change rapidly in space and in time. All right, so this flow through reach could be migrating up and down or changing from a losing to a flow through. All right, so these interactions change both in space and time. And one location here might be gaining during one portion of the year and losing during another. Let's talk about, there's some other interesting features here. These flow paths here. So this flow path right here originates in the stream, comes out into the alluvial aquifer, and discharges back into the stream. All right. In general, we're going to call this hyporheic flow because I use the pool definition of hyporheic flow, and that is any water that was stream water and flows through the alluvial aquifer for whatever length it is and comes back into the stream is hyporheic flow. Now, this flow path length, like these guys, could have been stream water 5 kilometers upstream. So these flow paths can be quite long. They can be kilometers long in the alluvial aquifer. But any flow path that originates from stream water, comes back into the stream, we're going to define as hyporheic flow. And it can be kilometers long.
So this hyporheic flow, could it skip a bunch of these kind of like regional flow?
It can skip, sure, it could, you could, as an example, I may have a flow path here that kicks out. Well, I can't cross flow paths, but I'm going to get rid of that one. As an example, these flow paths here could have come from the stream quite a ways away, all right? And they've missed this gaining section, but they're coming in down at this gaining section. So there's, within these rivers, I'm going to draw this river now in profile. So this is map view. Let's draw this river in profile. Okay, so this is going to be the profile of the river. Oh, I got to redraw this. What is going on with my... All right, so let's say water is flowing downstream. This is my vertical profile this way. All right. I can have hyporheic flow that are short flow paths, some that are long. So much like our we have both short hyporheic flow paths and we have long ones. And we have this nested flow. We call these nested flow scales, just like in Tothian in the groundwater basin. Along a stream, we have these same types of nested flows. We have very short hyporheic flow paths, so ones that might, you know, originate right here and come right back into the river. These can be very short, even over like a ripple scale, so over a couple centimeters. But like here, I might have one that just originates right here and comes right back into the river right there. All right, so these can be from centimeter scale to kilometers or tens of kilometers. Traditionally, when you read papers, most stream ecology papers think of hyporheic flow as these very short. So this I'm going to call traditional hyporheic flow. But these longer ones, they are not generally considered, especially by stream ecologists, as hyporheic flow. And there's some gray area, who knows what the flow path length is, where they would now call this alluvial groundwater flow. if you use the Poole, and Dr. Poole is a professor at MSU he's really done a lot of work in hypereal flow. He did a lot of his work with my predecessor, Dr. Wustner at UM. And they looked a lot at these, at gravel bed rivers, especially in the Intermountain West, where you've got these really long hypereal flow paths where you can have stream water that enters your groundwater system and stays in the alluvial system for a long time before it comes back into the stream. So Poole calls these, the Poole definition would say anything that is stream water and comes back into the stream is hypereal flow. Then there's another school of thought that says, I'm going to give it sort of a longer than 100 meters is alluvial groundwater. This is a gray zone, I'd say, in the scientific literature right now, whether this is alluvial groundwater or hypereal flow, whatever you want to call it. I prefer Dr. Poole's definition because it's very simple. If it is longer, if it comes from stream water, it's hypereal flow.
Hey, Peyton, what's your opinion on, so I've heard the hypereal zone be defined as like groundwater that has at least 10% of surface water containing within it. That's 10% might be a shot in the dark, but what is your general opinion of that definition?
Yeah, well, first of all, I think that's an incredibly hard definition to uphold, because then you've got to decide what is groundwater and what is surface water. So in these systems like this, where you've got exchange over a variety of scales, is this groundwater down here? If it's traveled 100, 2 kilometers in the alluvial system, is that groundwater now, or is that still stream water because it came from stream water? So I don't know. I mean, in general, they're thinking about, say, some zone like here, where you've got these rapid sort of circulation systems, and that's clearly stream water. And then there's some older upwelling water, even though it came from stream water some time ago. Functionally, Colton, I don't know how you could possibly make the distinction with that definition. But just like if I go in and we'll talk about this in our next little in-class exercise, but I don't know how I go in here and I take a packet of water and I say, hey, this is 10% groundwater and 10% and 90% stream water. Like, how would you even make that? How would you even tell that? Chemistry? Probably.
Yeah, that's a good point. It's hard for me to imagine when a hypereal flow path is 10 kilometers that's like still a hypereal flow path. I mean, I understand from stream going back into stream, but after that distance, it seems pretty it just seems like groundwater at that point, or is undistinguishable from most of the groundwater flow.
I agreed. Agreed. The question is, what's the scale then? Is there some magical flow path length? Like, is it 100 meters? Or is it 200 meters? Or is it 1 kilometer? Like, where do you draw the line that it's groundwater versus hypereal water? So there's a ton of gray. The only clean definition is Poole's definition. If it was stream water, and goes back to stream water, it's hyporheic flow. That's the only one that's very clean, easy. The other ones are very gray. And I don't, you know, this is a conversation in the scientific literature right now, for sure. But the bottom line is, for this class, hyporheic flow is this water that is moving from the stream back into the stream, all right? And what I want you to know is that it occurs over various scales, all right? And that the stream is interacting, the interactions are not, it's not like the Clark Fork is losing or the Clark Fork is gaining. The Clark Fork may be gaining over a section of 100 meters and losing over the next 100 meters. And those reaches have different groundwater stream water interactions that change both spatially and with time. So what is a gaining reach in August may be a losing reach in May. I would say that the traditional view of groundwater stream water interactions has been very static. So we have a gaining reach or we have a losing reach. And I would say the future of groundwater stream water interactions is thinking about how dynamic these changes are and what that diversity both in space and time means for the functioning of the river. Okay. So I want to take about, let's do 10 minutes. I'm going to send you guys out into breakout rooms. And here's your class exercise, your discussion exercise. All right, so you guys are going to have your own little consulting firm. All right. And there's a reach of the Clark Fork. Just west of Missoula. And there was an old paper mill. All right. And they put a lot of bad stuff into the alluvial groundwater system here. The question your clients would like to answer is, what are the groundwater stream water interactions? In this reach. Okay, so if we added a bunch of contaminants from paper processing into our alluvial groundwater system, all right, it's pretty important to think about whether this thing is gaining or losing to the groundwater system. If it's gaining, okay, if we've got a gaining reach, then contaminants are going to come into the Clark Fork, and we got to worry about that. If it's losing, could be losing, well, stream water's going this way, and we might just be taking contamination away from the Clark Fork, and we don't need to worry about it. All right. So your client comes to you and says, look, we need to know whether the stream reach is gaining or losing. How much groundwater is it gaining or losing? All right. So your job is to come up with what I call a white paper or a elevator proposal. All right. So they're going to call you up. They're going to say, hey, Hydro Consulting Group, what would it take to measure groundwater stream water interactions? What would you do, and how long? What methods would you use? All right. So you've got like a 5-minute pitch, 2-minute pitch to tell me what you're going to do to tell me whether this is gaining or losing. All right. Okay, so let's see. I'm going to stop my share. I'll look at breakout rooms. So we're going to do 4 rooms. All right, so there'll be groups of about 3 or 4 people. And we'll do 10 minutes. So at 9:30, we'll come back. So you got 10 minutes. Think about what methods you would use to tell your client, me, whether this stream is gaining or losing. All right. I will drop in on rooms as we go on. There you go. Okay, so we're back from our discussion groups. So let's I want to hear you get your 2-minute proposal to me for each group. So we'll start with group 1. What do you guys want to do? Yeah, give me your 2-minute proposal.
Well, the first thing we decided is we need to know, we're not sure if the stream has the contaminants yet. So we wanted to test the water, do some chemical tests to make sure if the water was contaminated or not. If it is, then we know right off the bat that one of the other things we wanted to do was either look to see if someone had tested for hydraulic conductivity, or we would drill a core ourselves and test for hydraulic conductivity. And the reason for that is so that we could measure inflow or outflow from the stream. I think that's pretty much what we had. I can't think of anything else right now.
Okay, so I'm gonna throw up. So group 1. Sharing my screen. Group 1 wanted to test for contamination.
Yes.
And find hydraulic conductivity.
Yes.
Okay. All right, group 2.
Sorry, I'm muted. We were thinking, like, instead of, well, first off, we were going to just look at the topography of the area and see if perhaps the river is like experiencing a time of relatively low change in elevation. So we could say maybe if it's like above a waterfall or above some rapids, perhaps it's losing water right there. But if there's nothing obvious like that, then we would drill a well and see if there's, and just use the measurements of head between the river and the contamination zone to see which direction the water is flowing. Is there anything to add, Emer or Amanda?
No, I think you got what we all said there.
Okay.
Yeah, nice.
All right, group 3.
Okay. We discussed also drilling some wells, but more or less creating a network of wells and or piezometers, lateral and down gradient from the paper mill, and to also track stream stage within the stream as well, and to track those throughout multiple seasons to track how head gradient changes throughout the seasons, and whether, as we were discussing before, whether it's how it's changing between gaining, losing, or flow throughout time. And then you could also track some hydraulic conductivity values from those wells, doing some slug tests, and get some porosity values from the sediment. And then you can determine flow velocity. And so you can even tell how long the contaminant would even take to get to the stream if it was gaining or was entering the stream.
Okay. All right. Group 4.
Since we're in the Missoula aquifer area, we knew that we're in an alluvial floodplain, so we kind of assumed that the hydroconductivity is likely high enough. But so we also wanted to think about the temporal aspect, like is it spring, summer, fall, etc., and what that may imply for gaining and losing reaches. But we figured that probably one of the easiest ways to determine if the contamination is going to get over there is drill a series of wells, maybe like 3 or 4 by the paper mill, and then 3 or 4 by the river, and just measure the water table height, and that should be able to give, and with continuous monitoring can be able to tell where the contaminant.
Okay, so I lost Andrew, but well network, some by the paper mill, some by the river, and monitor those water levels.
Just as well, Pat Payton, could you add in because it's a paper mill and they're going to have their own wastewater treatment setup, you could calculate their own, what the values are there, and it's recharge of that contaminant water back into the ground itself from there. So you could also tell how, what way it's moving.
Are we going to assume that it has a wastewater treatment?
I think most of them are regulatory. They have to have a wastewater treatment.
Yeah,
Okay.
yeah. You have to have, you definitely have to have wastewater. One thing about this, this doesn't pertain to this, and this is a great idea, but the mill has been closed down now for about 10 years. So so while it used to have a huge wastewater treatment plant, that's now been shuttered. However, you could still look at the records and look at how much recharge occurred. And that'd be an important thing to look at. Okay. All right. So some good ideas here. Group 3, which really was a a loaded group because they have a couple graduate students working in this area, definitely would have won the bid.
Okay.
Group 1, well, I didn't ask you to test for contamination. I wanted to know whether it was gaining or losing. So don't answer a question I didn't ask you to.
Okay.
And then
wait. We were going to use that to find if it was gaining.
That's actually okay. Fair enough. That's a good idea. And that's using a tracer. So fair enough. That's a good point. Let me just tell you how this works. You find bad stuff in the river. All right. Here is exactly what, and I'm going to tell you this is exactly what's going to happen and what will happen. The company that then owns the land now that the paper mill's on says, well, that stuff was in the river. It's not from us. It's from upstream. It's from Missoula.
Okay. That's true.
That's exactly what they do. That will be exactly, I guarantee it, 100% certain that will be their first response. That's not from us. That was already there. You have no way to prove that contaminant came from the floodplain right here. There's no way you can prove that. Now.
And you drill a well.
Until you drill a well. All right. So.
Yes. I messed up because I didn't we did have a couple other things we were talking
It's
about
a,
drilling
you know
wells.
what, I don't want to actually get into it. Everybody, like actually looking for a tracer, it would have been my first, that's what I do. All right, so you could use the contamination as a tracer. The topographic analysis is interesting. Topography and hydrology, while similar, are different, but drilling a well and looking at the head gradient is a good idea. I think some things that the group 3 did that was very thorough. First of all, we need a well network, all right? Both 3 and 4 had well networks. It's really going to be hard to tell anything from one well.
Okay.
Monitoring both heads in the well and the stream stage is critical, right? Because these are going to change dynamically. So you're going to want to monitor both of those. We need head and K, all right? So you got to do both of those and N. So, you know, most people had drilling a well. The fundamental thing we need to do is look at the difference in heads between the alluvial groundwater system and the adjacent river, and we need to do continuous monitoring. Right? So those are all really good points. So, I mean, everybody had good ideas and essentially honed in on, you know, what we need to do. And the first thing we need to do is investigate the changes, or the difference in head between the groundwater system and the stream water system.
Yes, sir.
Yeah.
I know that when we went to Lolo last year for the last year's class, we had the river piezometer and then we had the several wells. Is that why we had the multiple wells as well as the stream stage gauge?
Exactly. So we're going to look at, as an example of this kind of analysis, we'll look at some places in Lolo Creek where last year we got, and this year we would have gone on a field trip, but we'll still deal with some of the data and think about why they set up their investigations like they did. But basically, they were doing what you guys suggested: drilling a well network, monitoring both the well network and the stream stage, and trying to think about interactions between the groundwater and the stream water. Thursday, so for a lot of what the class, for the remainder of the class is talking about things like, well, how do we drill wells? What data is in the well, in the drilling of the well, that we can use? So how are we going to characterize the stream? So drilling methodologies and then characterization of the aquifer. So one of the things we'll talk about is we have this magical let's measure K from wells. And Colton threw out this idea, most of you probably don't even know what this is, as a slug test, right? That's one way we could try and get at K, but there's a whole lot of complexity in how we get this K value. And so we'll talk a lot about how we would actually measure hydraulic conductivity. So a lot of what we're going to do now is think about the methods of measuring hydraulic conductivity, of drilling and installing these, and actually trying to solve some of these problems. Yeah. Was that a question I saw? No? Okay. Okay, so I wanted to just go back and hit a bit of why it's so important to think about a well network. So let's go back to this map view, right? And let's put our hypothetical paper mill right here. All right. And let's say I drilled one well right here. I would measure between the river and my well right here. I would say, hey, this is a losing reach. All the water is coming out of the river and into the alluvial groundwater system here, and there's no chance of contamination. All right. But in reality, what's happening is my bad stuff would be following this flow path and coming into my river down here, right? So I need to have a well network. I need to have wells down here, over here, and over here, and over here. And hopefully, preferentially over here, and over here, and over here. Okay, so in a perfect world, you drill a ton of wells. But we're going to talk about this later. It's really expensive to drill wells. So as a consultant or a researcher, you're always fighting this battle that you want and need more wells, but you can't afford more wells. So a lot of what we do is think about, well, what is the most important set of wells that we could measure? So, like some, group 4 actually had some ideas. Well, let's put some wells right near the river and some wells right over near the plant and look at the difference. But it may be better to have them spread out farther away so you get a bigger picture. That there's no simple answer to that, but that illustrates why we need a well network. We can't just drill a single well. We're gonna need more than one well to think about this.
So like say, according to your picture here, you have the contaminants entering farther down the stream. So what would be a good distance for, say, the farthest well that, in order to truly capture whether or not would 1 kilometer from the plant be too far or not far enough?
There's no simple answer to that question, Mark. It's not like I can say, hey, 1 kilometer is far enough. The real answer is that you would drill, 3 or 4 wells to get you started, or look. The first answer is that probably there's wells in the area that you could use to start to draw an initial potentiometric map and think about where you need new wells. So in this example, I would say, hey, the farthest downstream I need some wells is down here. I need a well down near the discharge zone. But that's because I magically knew where these head contours are. In real life, you don't know that, and there's no real way to just lick your finger and say 1 kilometer is far enough. It could be longer than 1 kilometer, or it could be a lot shorter. There's no direct way to know that without looking at background information. One other, with the minute we have left, I also want to say that one other place, and Colton talked about this, but one other place that's a really good spot to measure whether your stream's gaining or losing is in the stream itself. And you can pound what we call piezometers. And this is a way to put a small well in the stream bed itself, all right? And we look at the elevation of the groundwater table in that piezometer compared to the stream. So like in this location, I would pound a piezometer and my water level would be below the stream bed or the stream surface. Let's say this is the stream surface. In these discharge locations, my water level in my piezometer would be above the stream surface. So these piezometers, whenever we're doing a groundwater stream water interaction, this is a really common method. We just take small pieces of PVC, we pound them down into the stream bed, and we're looking at the head in the water just beneath the stream bed and compare it to the water level in the stream itself. And that gives us an indication of gaining or losing conditions by looking at these piezometers. Now, it's really, really hard to keep a piezometer in a big river for very long. So this is a great method when you're working in a swamp that doesn't have any flow and is nice and sandy and soft, so it's easy to drive piezometers. But when you're in a big gravel bed river, it's going to be A, hell to pound the piezometer in gravel, and then B, it's going to last for maybe a couple hours before the river rips it out. So we have some issues, but we can do these, pound these piezometers. All right, so I will post homework today, homework 5, and then Thursday we're going to start talking about how do we characterize these systems. So the first thing we're going to do is talk about drilling and drilling methodology and what we can get from looking at and logging drill cores to help us answer these kinds of questions. So I'm done lecturing. So if you guys have any questions, I'm happy to stick around and answer them. Otherwise, we will see you on Thursday. Cheers.